Now, let's talk about the fifth section, which talks about electrons and the electromagnetic spectrum. So, in the vocabulary, by the end of this lesson, you should know all these terms, which are the Rutherford model, Bohr model, energy levels, constant, electromagnetic radiation, electromagnetic spectrum, wavelength, and frequency. Now, we've talked about electrons a little bit already, and but more specifically, back when we are talking about the atomic history, we researched on Rutherford and what his contribution was and what the model that he came up with looked like. So it was something like this, where we had um, an atom of gold foil being bombarded by alpha particles, and we saw that a lot of those alpha particles they passed right on through. They weren't stopped by anything, but sometimes we would get a deflection of those alpha particles, and they would bounce back at the source. And so that was weird. And what Ernest Rutherford came up for his explanation was that atoms have a nucleus. It's very densely packed, and it's located in the center. Now, we remembered from the cathode ray experiment and J.J. Thomson's contribution that all of matter had this type of subatomic particle that was negatively charged, and those were the electrons. But in Rutherford's model, there wasn't really a place to put them. They were just somewhere inside of the atom. Now, then came along Niels Bohr, and he refined Rutherford's model a little bit, and he introduced the electrons that were um, that were found in these sort of rings outside of the nucleus. And you can see that in this model, we have two electrons inside this inner ring. They're inside of that line. And then in the next one, we have another electron. Notice that there's nothing in between these two rings. There cannot be any electrons in that section. All right, and so that was Bohr's contribution to it, is that he came up with the idea that electrons, they orbit the nucleus in fixed paths, right? They have to be inside of this ring. Well, not inside, they have to be directly on the ring. They can't be in the space between them. So it was a lot like the solar system. It's called the planetary model, where again you have the sun. You can think of it as being the nucleus of the atom or the nucleus of our solar system, and you have all the different planets that are in orbit around them, and they have a very specific path that they go through, and they don't really get in each other's ways. All right, now these orbitals that Bohr came up with, they present the different energy levels, and so we know these electrons will have different levels of energy, and that's really all we'll talk about. Later on, if you get into quantum theory, you learn that the atomic orbitals they don't really look like these rings. They really look more like these more complex shapes, depending on what energy level you're looking for. But that just gets really technical and really complicated. The thing about quantum theory is that it's weird and it's confusing, and we're not going to deal with it too much. We're just going to stick with the Bohr model because even though it's not technically correct, it helps us to understand a lot more what the electrons are doing, especially when it comes to bonding. So I just get familiar with the Bohr model. We'll be using this a lot more later on. But just remember that technically not correct, but it's a useful way of visualizing our electrons in atoms. All right, so we just talked about how the electrons are found in these energy levels. So let's talk a little bit more about that energy that the electrons have. So a lot of the energy that we can see that we're familiar with is in the form of electromagnetic radiation. And this just some type of energy, a form of energy that has a wave-like behavior as it goes through space. So let's talk about waves a little bit more. So the different examples of waves that you've probably heard of is there's light, we have radio waves, X-rays, we have gamma rays, and ultraviolet light, infrared light. So all these terms you've heard them before, but they're really types of electromagnetic waves that we can measure and understand. So now all the different types of electromagnetic waves, they're a part of what we call the electromagnetic spectrum. So that's what stretches from radio waves, which are very long, low energy waves, all the way to our gamma rays, which are very short waves that carry a lot of energy. All right, so now let's talk about the parts of a wave so we can talk about waves a little bit more specifically. All right, so first of all is that they have a repetitive nature. So the way that this looks is that if we start looking at our wave here, we can go through the cycle, and so we can go that it goes up and then it comes back down. And now this point is really the same as this point that we started with. So we would call that one cycle. And so see that it repeats the same thing. So we have the same wave we just went through. It just repeats itself again. It goes up, it peaks, and then it falls back down to that same starting point that we have. Now this line that is dissecting it, it's not really part of the wave, but it's just what we call the origin. So we know that from this point, the wave can go either up or it can go down. And every time it'll be going the same height. Now, whenever we peak on a wave, we have the crest. So these are the peaks that we have in the wave. We call those crests. And then the valleys at the bottom, they'll be called troughs. And we also have the node here, which is just whenever the wave crosses the origin, this is when it has a value of 0. And so it can go into a positive slope on this, or it can go into a negative slope. But when it's 0, we call that a node. And then we can find more sections on the wave as well. So the height that it goes through, that is called the amplitude. And so the amplitude can be either positive when it goes to a crest, or it can be negative when it goes to a trough. And then the space or the length between two of the same points, so either between two crests, between two troughs, or between two nodes, this is what we will measure as the wavelength. And so the wavelength, in the technical definition, is just the distance between two corresponding points or on adjacent waves. So again, if this is one wave, goes up, goes back down, that's one wave complete. If we do it again, the bottom point, this is the second wave. And we can measure either from crest to get our wavelength. We can measure from trough to find our wavelength, or we can go from node to find our wavelength. And that distance will be the same every time, no matter if you're looking at crest, at a trough, or a node, as long as the 2 points are the same. And all these waves, we'll measure them in meters, centimeters, or nanometers. And so we're measuring the distance between the 2 points on our wave. Now, the wavelength we are going to represent it by this symbol. It looks like a very fancy H or an upside down Y, maybe a tippy. And this symbol is actually a Greek letter, and it's called lambda. So when we start getting into the mathematical formula, we're not really going to use the word wavelength. It's a little lengthy, or it's a little long to write. So instead we'll be using the symbol lambda. All right, now we can compare different waves too. So we've said that they have a repetitive nature. So now notice here that the number of waves that I have drawn on this diagram. So here I would have, let's see, that's one wave with going from our starting point, going to the first trough. We can go through another one. This is 2 waves. At the second trough, keep going, 3 waves. 4 waves, then one more, 5 waves. So can we take it all the way to 6 waves if you were counting troughs? You would get the same if you started counting nodes or if you were counting crests. Now, the number of waves that we have in a certain space or in a certain time interval, we call it the frequency, just how many times it repeats itself over this amount of time. So let's see. And the unit that we use to measure our frequencies, that we can use waves per second. We can also count that as cycles per second. We can also use the word hertz. So you've heard hertz for counting maybe the pitch of a certain sound, of a certain tone. And then finally, we can also use seconds inverse. So seconds to the negative first power is another way of measuring the frequency of our waves. Finally, we'll use the symbol F for frequency. So this one's pretty simple frequency. The word starts with an F, so we'll use the symbol F. It's not as confusing as using the Greek letter lambda for our wavelength. All right, we can compare different waves as well. So I have 2 waves on here. We'll assume that they are happening over the same amount of time. So we'll say that this is 1 second. And this is how many waves we're getting 1 second for this type of wave, and then for this second type of wave. So now, notice that we have different wavelengths, the space between the 2 same points, between peak to peak, or node to node, trough to trough, in these two waves, they're different. They're covering different lengths. But notice that in this top one, these waves are a lot closer together, and we have a lot more of them in the same section as opposed to this one, where we only have two peaks in this one. So we have two cycles on this, and the waves are a lot farther apart, and we have less of them. This is because the wavelength and the frequency of a wave are inversely related. So that means that if one is goes up, the other one goes down. So if you have a high value of one, you have a low value of the other one. All right, so if we compare these two in this wave, because we have so many cycles, if we go through and count them, so we have here one cycle, two cycle, three cycle, four cycle, five cycle, six cycle. So it's a very frequent wave, so it has a very high frequency, and the distance between these waves is very short. So we would say it has a short wavelength. Whereas if we compared it to this one over here, we can say how many cycles. So this is one cycle and two cycles. There's only two cycles on this one, and notice that the waves are a lot more spaced out. So in this one, we say that we have a low frequency. We only have two cycles on this, but these have a very long wavelength, right? These waves are more spaced out from each other. Now let's talk about energy as well. These waves relate directly to their frequency. So a wave that is very um, low in frequency, it will carry low energy. And if it has a high frequency, it will carry a high energy. So think of it this way. If you're going to tap out a rhythm and you just tap on the table very slowly, you can tell that the time between every tap here is very long, and it doesn't take a whole lot of energy for me to tap at this speed. But if I were to reduce the time between my taps and make it more frequent, again, I'm tapping a lot faster, and this is taking a lot more energy for me to keep up this speed. And if I were to go even faster, my hand gets tired very quickly from that. All right, so it's taking me a lot more energy to keep up the really fast tapping as opposed to the very slow tapping. And so it's the same that happens with a lot of these waves. So a wave that is very frequent, it has a high frequency, it will have a high energy. And a wave that is not very frequent, it has a low frequency, will have a low energy. All right, so now we can bring back this diagram that we are looking at before of electromagnetic radiations, and we can see the different types of waves that are on here. So we can have the radio waves, which have very long wavelengths. So they're about the size of buildings, and even bigger than buildings as well. And so these are the same radio waves that carry information. They're what play the tunes in your car stereo, and it's what we use for communications. So things like Wi-Fi and Bluetooth and cell phone communications, all of those are based on wavelengths, and they don't carry a whole lot of information. Sorry. They carry a whole lot of information, yes, but they don't have a lot of energy. So that's why it's very safe to just carry them in our pocket, like our cell phones. Now we move on to something that is a little bit with a higher frequency and a shorter wavelength. We have the microwaves. So it's just like the microwave oven in your kitchen. You can use those microwaves to heat up your food. So you're heating up the food, you're creating more energy within the food. That's what makes it hotter. And we can move on into infrared. So if you ever seen maybe night vision camera or night vision goggles, those are using infrared light in the environment to pick out to pick out uh, things that you can see. Now, you know that you can't see that infrared light, so we need those special instruments to pick up on the infrared light. So if we move closer to this side, we get to the visible spectrum, and so this is where you can see all the colors. So notice that in this one, we start from the dark side on here on this slider, and so then it turns into red. So this is the range for infrared light. We can't see it uh, with our human eyes, but there is some type of light there that can be picked up by special instruments. And then we get here into the different colors of the rainbow. This is the section of visible light. This is what we can see with our eyes. So it's what we can recognize as different colors. And then we get into this pinkish section where we have the ultraviolet light. So you've heard about this, that when you're on the sun, you need to protect yourself from the ultraviolet rays. You use sunscreen in the summertime, which has a UV protectant, or if you look on your weather app, you might see the UV index for a certain day. You know that UV radiation can give you cancer, and so it's because this is a type of wavelength that carries a lot of energy, enough to damage your human cells. And move on closer to X-rays. If you ever had a radiograph taken, it's using X-rays, and so you know that usually you have to put on a lead vest to protect yourself from those X-rays because they carry a lot of energy and they can be very damaging to your cells. And finally, we get to the gamma rays. These are the waves with the shortest wavelength, and they carry the most amount of energy. And so where we commonly find gamma rays is in supernova. When stars die and they explode, they let off uh, this huge wave of, no, I shouldn't say huge. They let off gamma rays, and they carry a lot of energy. And sometimes, if a planet is too close to the supernova, if there were to be life on that planet, it would be completely wiped out because these gamma rays are so powerful. They carry so much energy. They could literally be used as a weapon. All right, so just a little bit more on these electromagnetic waves is that these all travel at the speed of light because the visible light that we can see, it's a type of electromagnetic radiation. Well, the same speed of light applies to all types of the electromagnetic radiation. It doesn't matter what their frequency or what their wavelength is, they will always move at the same speed, which is 3.00 times 10 to the eighth power meters per second. So it's about 3 billion meters per second is how fast light is. It's the fastest thing that we have in our universe, and there's nothing that can go faster to our knowledge. Um, Now, the speed of light here, again, we'll be using the symbol C for the speed of light. And so the speed of light will always be a constant. This means that no matter what type of problem we see it or when we're talking about it in different scientific contexts, it always has the same value. So every time that you think of the speed of light, always think of this number of 3.00 times 10 to the eighth power meters per second. It will always be the same because it is a constant value. All right, so now we can take all this information and we can put it into a mathematical formula that relates all these together: the speed of light, the wavelength of a wave, and the frequency of a wave. And it looks like this, where C is equal to lambda F. So this is the wavelength formula, and we can use this algebra formula to find the different information of a wave if we know just one of the other pieces. All right, so to break this down into words, if you can't remember what these symbols are, we have the speed of light is equal to the wavelength of a wave multiplied by the frequency of that wave. So let's look at some examples of how would we actually use this formula. So if you have this problem here, so what is the wavelength of a microwave that has a frequency of 3.44 times 10 to the ninth power hertz? All right, so don't forget that we'll need this expression. This is just an algebra expression we'll be using. And I know that it can look kind of complicated, especially when you think of this problem of microwaves and they have a frequency of 3.44 times 10 to the 9 hertz. But if you just follow along, you'll see that this is just a simple algebra problem. You'll either be dividing or multiplying two numbers together. That's all it takes on this problem. All right, so what you should do first is to write down the information that you know. So you know that the speed of light is a constant, so it will always be 3.0 times 10 to the eighth meters per second. You don't need to be told what this number is. You should always just bring it back, remember it, because it's a constant value. So next, we know the wavelength. We don't know what this is. This is what the question is asking us. What is the wavelength? So we want to solve for what this symbol lambda, the wavelength, that is our unknown. We want to solve for that. And then lastly, we have F, the frequency. We are given the frequency. It is 3.44 times 10 to the 9 hertz. Now, hertz, that might throw you for a loop a little bit, because if you look at the units we have so far, the speed of light is measured in meters per second, and our wavelength is measured with meters. So this hertz doesn't match the meters that we have in both these, and it doesn't match the seconds. So what I do is that I eliminate the hertz. I forget that I'm even using these, and instead I replace it with seconds to the negative first power. You'll see why this is important in a second. All right, so now to solve for this wavelength, it's tied together to frequency by multiplication. So we just want to do the opposite operation in this. So we'll take our frequency on this side and divide it by the frequency to isolate the wavelength. And following algebra rules, what you do to one side of the equal sign, you have to do it to the other as well. So we'll take our speed of light side and divide that by the frequency. Now notice that we have two matching values in this expression. Here we have frequency divided by the frequency, and so because they're the same, it's like saying that they're equal to 1, so we'll just cancel these out. Frequency and frequency will cancel out on this side, and so we're only left with speed of light divided by the frequency is equal to the wavelength, and so that's our new expression that we'll be using. So now we can just take the information that we know, the speed of light, 3.00 times 10 to the 8th power meters per second divided by 3.44 times 10 to the ninth power seconds inverse is equal to our wavelength. Now, again, make sure that you are always looking for matching units to see what your final unit will be and if it's the one that you want. So in this case, notice that I have seconds in the numerator and seconds in the denominator. They're matching, and so I can cancel those two out. And then meters, I have one in the numerator, but I don't have any meters in the denominator, so I can't cancel out the meters. That's telling me that my answer will be something measured in meters, which actually my wavelength is measured in meters. So this is how you can check to see if you've set up the problem correctly. So now all that's left to do is that you have these numbers, 3.0 times 10 to the 8th power and 3.44 times 10 to the ninth power. All you have to do is calculate these, put them in a calculator, and you get the result of your wavelength being 0.0872 meters per second. All right, so real quick tip on the calculator on how to do this without messing up your numbers, because a lot of our calculators are really picky and they'll give you different answers if you don't put it in exactly right because of the order of operations that it reads through it. So again, here's my problem that I had in the last slide and the result that came from it. And the way that I got it is that using our calculators, I put in my number 3.00, and then for the scientific notation part of it, I didn't type in times 10 to the 8th power because that's going to mess up your order. Instead, I used the special symbol E on my calculator. And so that represents scientific notation, and it's the same as saying times 10 to some power. You just have to put in the exponent number right at the end. And the way to get this is that you have to press the second key in our calculators and then press this X -1 key, because right above the second function that goes with it is this double capital E symbol. That's the key that we use for scientific notation. And when you do it this way, you won't mess up the order of operations in these problems. So this way I can put in 3.00, second E key, number 8, to put in my first quantity, and then I can divide that by the second quantity, doing the same thing. 3.44 is the value that I have, and then I will, instead of doing times 10 to some power, I will do second E key, and then put in my ninth power. So pressing that 9, and this is what I get. And just pressing enter gets me out this answer of 0.0872 meters is the wavelength of my problem before, which was, let's see, what is the wavelength of a microwave with a frequency of 3.44 times 10 to the 9 hertz. I changed hertz into seconds inverse. I used my wavelength expression to cancel out frequency so I can solve just for wavelength. I put in my numbers and I get out the result of 0.0872 meters as my wavelength. Other than that, this wraps up our whole unit. So make sure that you've kept up with all this, that you've taken all the quizzes and turned them in, and make sure that you show me your notes when you're finished with this.